Pluto is a remote and baffling, more unobtrusive planet that was once part of our Sun's planetary system, but was later reclassified as a dwarf planet. However, surprising revelations by prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They proposed that this cold world is on a potential collision course with Neptune. But how could this be possible, and what would be the consequences of such a monumental event? Is this an interesting cosmic anomaly, or is there something more to this approaching celestial drama? Join us as we examine the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet partly due to its strange orbit, remains a subject of great interest and study in the astronomical community. Recent studies by leading researchers show that Pluto's orbit is dangerously close to Neptune's. Both Tyson and Kaku have sounded the alarm about a potential risky crash between these two bodies, which could pose a serious threat to Earth. So how is such an event even conceivable? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an astounding 248 years to complete a single orbit. Since its discovery in 1930, it has not yet completed one full revolution. However, the curiosity surrounding Pluto doesn't stop there. Its orbit is marked by an especially elongated shape, wandering far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, which is tilted at 17 degrees to the ecliptic plane. How Pluto moves is substantially more inclined compared to other planets, adding complexity to its orbital path. One of the most fascinating aspects of Pluto's orbit is its convergence point with Neptune's orbit. For about 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, challenging our expectations about their positions in the planetary system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The assessment of Pluto's orbit began shortly after its discovery. Astronomers initially struggled to understand its peculiar path, especially in comparison to planets whose orbits are close to the ecliptic plane. Pluto's orbit stood apart with its steep inclination and elongated shape. The mystery deepened when it was confirmed that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricate design of space mechanics. The three-body problem in space, determining how three objects like Pluto, Neptune, and the Sun interact gravitationally, is a fundamental concept in space physics. It's akin to predicting where they will go based on their starting positions and gravitational pulls on each other. In Pluto's case, this problem shows how the orbits of Neptune and the Sun's gravity interconnect in a complex way. Terms like libration, resonance, and chi oscillation are crucial in understanding this puzzle. Libration, in the specific context of Pluto and Neptune, suggests that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is key in preventing a collision between their orbits. Resonance, on the other hand, refers to the periodic movement of a celestial body within its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is arranged entirely above their orbital plane, providing an additional layer of protection. Another critical concept is the chi oscillation, named after three researchers, von Siepel, Kappas, and Lev, who studied how objects in space influence each other gravitationally. This oscillation helps explain why Pluto's orbit remains so stable despite its apparent eccentricity. Even though its path around the Sun appears erratic, Pluto's orbit remains predictable over billions of years, suggesting that its journey is governed by a certain order. Predicting cosmic events, especially when they involve the chaotic orbits of objects like Pluto, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While numerical simulations are valuable tools in understanding and predicting the future movements of celestial bodies, they also underscore the limitations of our predictions. These models rely heavily on the accuracy of initial conditions, and any minor deviation can result in vastly different outcomes, making precise predictions a daunting task. The complex nature of celestial orbits, like Pluto's, reminds us that our understanding of space remains far from complete. Understanding the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It demonstrates how the position and presence of each planet can significantly impact the stability and behavior of other objects within the system. But why are prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku raising concerns about a potential collision between Pluto and Neptune? Despite the many forces preventing such an event, Tyson, an influential astrophysicist known for his role in renaming Pluto, offers an intriguing perspective on the mysteries of our solar system. Tyson's commentary on Pluto's reclassification as a dwarf planet aligns with the ever-evolving knowledge of the solar system. He views this adjustment not as a demotion, but rather as a significant refinement in our understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning, and he sees the complexities of Pluto's orbit as evidence of how much we still have to discover about space. His work highlights that as we uncover more about the universe, more questions arise, pushing us to explore further and refine our understanding. Michio Kaku, a respected physicist and futurist, offers a different but complementary viewpoint. Kaku is known for his ability to link complex scientific ideas with visionary concepts. He emphasizes the chaotic forces that shape our universe and urges for continuous observation and advanced modeling to predict and understand potential cosmic events. Kaku views the potential collision between Pluto and Neptune as a reflection of the dynamic and often turbulent nature of space. He believes that studying the connections between celestial bodies is not just important for academic interest but also for practical implications. He warns that events like a Pluto-Neptune collision could have broader consequences, from impacting our understanding of the solar system to possibly requiring future space interventions. Kaku's futuristic viewpoint suggests that the more we understand these forces, the better prepared we will be to navigate and possibly mitigate major events in space. Both Tyson and Kaku emphasize that space is an area of limitless discovery, and while our current understanding is significant, it remains limited. A broad scientific consensus currently holds that the orbits of Pluto and Neptune will remain stable for years to come, thanks to their mean motion resonance and various gravitational forces acting on them. Therefore, a direct collision between Pluto and Neptune is considered highly unlikely. However, the complexities and potential disturbances in orbital elements mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may pose. While a Pluto-Neptune impact remains a largely hypothetical scenario, it underscores the importance of ongoing study and observation in space science. Advances in technology, including more advanced telescopes and computational models, will help astronomers refine their simulations and predictions. This ensures that we stay ahead of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming, along with Kaku's emphasis on the unpredictable nature of celestial mechanics, both highlight the need for continuous investigation and a flexible understanding of our universe. The potential impact scenario between Pluto and Neptune serves as a case study for the challenges and opportunities in space exploration, underscoring the need for effective scientific inquiry, cutting-edge technology, and a willingness to adjust our understanding as new data emerges. Pluto continues to captivate scientists and space enthusiasts alike with its distant and mysterious nature. While its status as a dwarf planet has long been debated, its orbit and unique characteristics continue to engage researchers. Recent developments have again positioned Pluto in the spotlight, especially with the possibility of a gravitational interaction between Pluto and Neptune gaining attention in the space community. With Tyson and Kaku bringing this topic to the forefront, discussions surrounding a potential Pluto-Neptune impact are sure to spark further research and inquiry. The study of these enigmatic celestial bodies holds the promise of uncovering new insights into the mechanics of our solar system. As we peer further into space, the dynamic and unpredictable nature of our celestial neighborhood emphasizes the need for vigilance and ongoing investigation. While the potential interaction between Pluto and Neptune remains a subject of scientific interest, it is essential to consider the broader context of space exploration and the methodologies used to study celestial bodies like Pluto. The discovery of potential risks, such as a possible Pluto-Neptune collision, serves as a reminder of the vast complexity and unpredictability inherent in the universe. This thought draws attention to the sophisticated tools and techniques employed by astronomers and physicists to understand the movement of celestial bodies. Numerical simulations, for example, allow researchers to model and predict the behavior of planets and dwarf planets over long periods. These simulations rely on input parameters like mass, speed, and distance of celestial objects, which help researchers assess the stability of orbits like Pluto's. Such models are particularly valuable when studying objects with unusual orbits, like Pluto, whose path around the Sun is distinct from the other planets in the solar system. Gravitational interactions between celestial bodies are another crucial element in understanding the orbits of distant objects. While Pluto's orbit crosses Neptune's, the gravitational pull between them does not lead to a collision, thanks to their resonance. This gravitational resonance ensures that even when Pluto comes close to Neptune, their orbits remain stable. However, the influence of other planets like Jupiter, Saturn, and Uranus could potentially disturb the delicate balance keeping Pluto and Neptune in sync. Over millions or billions of years, these shifts could accumulate and lead to more significant changes. In addition to gravitational forces, the Sun's gravity also plays a crucial role in shaping the orbits of objects in the outer solar system. However, because Pluto is so far from the Sun's gravitational pull is much weaker on Pluto than it is on the inner planets. This means Pluto's orbit is more susceptible to external influences. For example, the Sun's varying energy output over time could affect the behavior of objects in the Kuiper belt, where Pluto resides. These subtle changes could influence Pluto's long-term orbit stability. The study of Pluto's environment also provides insights into the outer reaches of the solar system. Pluto resides in the Kuiper belt, a region populated with countless small icy bodies and dwarf planets. As astronomers continue to gather more data from space missions like NASA's New Horizons, which conducted a flyby of Pluto in 2015, they are beginning to gain a better understanding of this distant region. New Horizons provided stunning close-up images of Pluto and its moons, revealing a complex world of icy mountains, vast plains, and strange atmospheric features. These findings are opening new questions about the formation and evolution of the outer solar system. As we continue to refine our understanding of Pluto and its relationship with Neptune, we must also acknowledge the broader implications for space exploration and future discoveries. The study of distant objects like Pluto helps us gain a better understanding of the history of the solar system and the forces that shape planetary bodies. Moreover, these discoveries can have practical applications for future space missions and human space exploration. With ongoing technological advances, our ability to monitor and study the outer solar system is expanding, opening new frontiers for exploration. In conclusion, while the possibility of a Pluto-Neptune collision remains highly unlikely, the fact that this scenario has captured the imagination of scientists and the public alike shows the continuing allure of the mysteries of space. The complexity of Pluto's orbit, the forces that shape it, and its interactions with other objects in the solar system all serve to remind us of the vast and unpredictable nature of the universe. As we continue to study these celestial bodies, our understanding of the solar system will deepen, revealing new insights and raising new questions. The case of Pluto and Neptune is just one of many examples of the wonders of space that continue to captivate us, urging us to push the boundaries of our knowledge and explore the unknown. The ongoing study of Pluto and its orbit will likely remain a key area of research in planetary science, as scientists strive to unravel the mysteries of this distant dwarf planet and its place in our cosmic neighborhood. While the prospect of a catastrophic impact with Neptune remains highly improbable, the potential for further discoveries and insights into the dynamics of the solar system makes the study of Pluto all the more fascinating. As we continue to expand our understanding of the outer solar system, Pluto remains an intriguing subject for both theoretical astrophysics and practical space exploration. One area of study that continues to evolve is the role of gravitational interactions between distant celestial bodies and their impact on the trajectories of objects in the Kuiper belt, the region where Pluto resides. This belt, which extends beyond the orbit of Neptune, is a vast collection of icy bodies, dwarf planets, and comets. These objects have been relatively stable for billions of years, Yet their orbits can be perturbed by the gravitational forces from the larger planets in the solar system, especially Jupiter and Neptune. The potential for these interactions to destabilize orbits, including Pluto's, makes their long-term behavior a key topic of research. Recent studies have also examined the possibility that the solar system may have been significantly different in its early history. Early on, the gravitational influence of giant planets like Jupiter and Saturn could have scattered smaller bodies into the Kuiper belt, shaping the current arrangement of objects like Pluto. This theory, known as the Grand Tack hypothesis, proposes that the outward migration of Jupiter and Saturn could have sent the primordial planets hurtling through the outer solar system, altering the positions of smaller bodies like Pluto and Neptune. This reshuffling of the solar system's architecture could explain some of the current orbital eccentricities we observe today. In addition to these gravitational factors, Pluto's atmospheric conditions remain an area of intense interest. Pluto's thin atmosphere, primarily composed of nitrogen, methane, and carbon monoxide, undergoes dramatic seasonal changes as the dwarf planet orbits the Sun. The changing atmospheric pressure and temperature cause the atmosphere to expand and contract, offering a fascinating example of how distant celestial bodies evolve and interact with their environment. NASA's New Horizons mission provided invaluable data, revealing that Pluto's surface is much more dynamic than previously thought, with mountain ranges, flowing ice, and vast plains, indicating a complex history of geological activity and atmospheric processes. The study of these distant worlds, including Pluto, challenges our understanding of planetary formation, evolution, and stability. As we refine our models and technology, new discoveries will likely continue to reshape our view of the solar system's past, present, and future.